Okay, so I posted homework for Wednesday. There's both online and written homework for Wednesday. Uh, don't wait till Monday or Tuesday to start that. Start work on as much as you can this weekend, and then you can have lots of office hours opportunities Monday and Tuesday to get your questions answered. It's not short. It's a lot of problems, but a lot of them are not very long. But it's not short. So do start this weekend. Okay, I also posted the raw scores from the multiple choice on Canvas so you can see what you got out of 30. We still have to, there's just a little bit more to grade on the free response, then I had to add the numbers and crunch the numbers, so it's still a little ways off until I can get you actual scores out of 100 on the second exam. Okay, and then next week we'll talk about, once all the scores are in, then we'll go over some of the most commonly missed items. You'll go over the free response and recitation, etc. Okay, so we're in the next module, which is sequences and series. Let's just quickly review. What is a sequence? What is a sequence? That's the list, right? That's just a list of numbers. Most of the time there's a pattern, right? And so there's these problems where you have to figure out what the formula is to give you the ith term of the list. And then what's a series? You just add them up, right? So this is like, this aspect of it is like first grade. Make a list of numbers, add them all up. So we don't want to lose sight of that, because when things get complicated and there's lots to remember and memorize, don't lose sight of the fact that we've got a list of numbers and we're adding them up, okay? All right, so the sequence is a list. Here's an example: 1, 1/3, 1/5, 1/7, 1/9. And we talked about finding a formula. Can you find a formula for this? So the ith term of this sequence is what? So what would the formula be? So they're all 1 over something, right? 1 over what? So this is, remember, write out your I values. So 2 gives 3. This is how you think about it. 3 gives 5. 4 gives 7. 5 gives 9. So what formula for I gives us that denominator? What do we do? You're going to multiply by 2 and subtract 1, right? So it helps to see by listing out the i's and then saying to yourself, okay, 2 gives 3, 3 gives 5, 4 gives 7, 2n minus 1. So you'll have plenty of practice of that in the homework. Okay, and then so this is the formula for the ith term in the list, and then so when I equals 1, and then I equals 2, and I equals 3, that makes the list, right? That makes the list. Okay, and then a series is where we just add them all up. We just take the values in the list and we add them together. And then we had this, so we talked about how a second grader would understand that. But that's how we need to think about it, right? So I'm emphasizing this, how would a second grader write it? Because we have to always think that way, think this way, because don't get lost in these scary symbols here. This just means this, right? So you see this, you think this. Okay, and then the sequence of partial sums. The first partial sum is the sum of the first 1 values of the list. The second partial sum is the sum of the first 2. The third partial sum is the sum of the first 3 in the list. The sum of the fourth partial sum is the sum of the first 4 in the list or in the sequence, etc. Okay, so now the sequence of partial sums kind of steps it up a level in terms of understanding and making sense of it, right? So that's slightly harder. Okay, that's slightly harder, but not bad, right? Okay, so let's. Any questions on the overview, our reminder of what we've done so far. So let's look at the back page of that handout I gave you. If you don't have it, it's okay. I'll put it on the screen. And let's just see how far you can make it in 5 minutes. See how far you can make it in 5 minutes. Do as much as you can, okay? So let's talk together. So a turtle is walking across your back lawn. Everybody's experienced this, right? And then on day 1, he starts at the east and he walks halfway across the lawn on day 1. On day 2, he walks half the distance remaining to go to get to the west end. So he walked a quarter of the total length. So on day 3, what fraction of the total length did he walk? On day 1, he walked half of the distance across the lawn. On day 2, he continues and walks a quarter of the total length of the lawn. So on day 3, he will walk 1/8. Okay, so just to make sure we got it. Every day he continues this way, always walking half the distance remaining to get to the west end of the lawn. Or another way to think of it is half the distance he walked the day before. So he always walks half the distance he walked the day before. So you're going to write the sequence, you're going to write the series and the sequence of partial sums, and then you're going to find the formulas for both sequences, the original sequence and a formula for the sequence of partial sums. Okay, see how far you can make it in 5 minutes. Go. Everyone's working on it. You're writing, either thinking or talking to somebody else. This is that pink sheet I gave you on, is it Monday? Back side of the pink sheet. Okay, so you should notice in the denominator you have, what, are these all perfect squares? No, but there is a definite pattern here. What's going on? What do we have? Powers of 2. So the ith term has what power of 2? This is the first, second, third, fourth. So the fourth term is 1/16. What power of 2 is that? 16 is 2 to the 4th. 8 is 2 cubed. So the power is really the same as what? The one that it's just I, right? So it's 1 over 2 to the I. So notice I've written that in function form, right? I've written that in function form. I could put it in a sequence form and do A sub I. Both are the same. But then you need the chevrons. Okay, so the series. You just add them up. You just add them up. That's what a series is. That's what a series is. It's just you add up the terms in the list. Okay? And so then in calculus form, sum as I goes from 1 to infinity of that. Yeah. The sequence formula. So that's what goes here. Okay, sequence of partial sums. What's the first partial sum? 1/2. Second partial sum? 1/2. Second partial sum means add up the first 2 in the sequence. So 3/4. Then add up the first 3. That's the third partial sum. Fourth partial sum, add up the first 4. So this is its own new sequence, right? The sequence of partial sums from our original sequence becomes its own sequence, and we can write a formula for that. So now we got a numerator and a denominator. 1, 3, 5, 1, 3, 7, 15. Maybe we should do one more. 30, is it 31, 30 seconds? So in the numerator, so this is capital S, it's the sequence of partial sums. So the numerator, so 1 gives 1, 2 gives 3, 3 gives 7, So this is 3, 4, 5. 5 gives 31. 4 gives 15. 3 gives 7. Maybe we should do the denominator first. I mean, that's easier. 1 gives 2. 2 gives 4. 3 gives 8. 4, that's the same thing we had before, right? What's that? 2 to the I. So the denominator of this new sequence is the same as the denominators of our original sequence. So that's the same formula. So then what is the numerator? Do you see how those numbers are always just one less than the denominator? So we just do the denominator. Subtract 1. And then we could write this as, split it up, 1 minus those are equal, those are the same. Okay, so what does the sequence of partial sums represent about the turtle? What's that?
How much of the lines reverse?
Okay, so what about, so you talk about the turtle, so. Yeah, it's the turtle's distance from the east end, or that, like, what, the accumulated distance. It's like, this is an accumulation function, right? This is the accumulated distance the turtle has walked in the first I days, right? So again, this is the exact same principle as an accumulation function. Same principle, right? So it's a function, but it's not a continuous function. It's a discrete function, right? It's only for values of I equals 1, 2, 3, 4, 5. So, and then in this case, the accumulation of distance. Okay, will it ever make it across? Will the turtle ever make it? Some are saying no, some are saying yeah. So in Monday, maybe we'll get to it, Monday or Wednesday. We're going to do the math, okay? So we're going to actually talk about this, so stay tuned.
Oh, the convergence test.
Some say no, some say yes. You can argue about it over the weekend. Okay, questions on A through C? Questions on A through C? Okay, so in your homework, so in the written homework, you're going to be using GC to model some of this stuff, and I'm going to show you how that works. So when you open up these files that are on the web page for your written homework, you're going to open up, you're going to see something like this. Okay, rather than I, GC uses K to be the index. K, so that's an easy switch. And so the turtle crossing along, we want to create the sequence and the sequence of partial sums, and we want to let GC do the work for us. Okay? Okay? So we start with the sequence. What was our formula for the sequence for the turtle? For the distance that the turtle walked on, and at this time now it's the kth day. What's the distance the turtle walked on the kth day? 1 divided by 2 to the k. And notice what's happening in the table as I do this. Boom, there's the sequence. I'm not sure how to make the table bigger. I would if I could, but there's the sequence. Once that table's set up for you, once you put in what S of k is, it tells you the distance traveled by the turtle on the kth day. So this was our 1/2, 1/4, 1/8, 1/16, etc. Okay, so now we want to do the sequence of partial sums. Sequence of partial sums. So we're going to, if you select the table and then go up to table here, you want to add formula. So we don't want to just add a plain column that we're going to like, column is like if you were going to enter your own thing. We want to add a formula. When you add formula, it'll make a new column here. And then our sequence of partial sums is capital S. And then use function notation. And the capital SK. And notice nothing shows up because we haven't defined what capital SK is. GC has no idea what we're doing. It has no idea about the turtle. It has no idea what we mean by capital S. That's what we're calling it because that's our convention. So now we have to define what capital S is. And this is going to be the kth partial sum. So how am I going to express the kth partial sum on GC? I'm going to write out 0.5 plus 0.25. I'm going to do that? No, because it needs to be the kth partial sum, right? So if we start adding these up, there's no way to tell it where to stop. So what can we use instead? Amanda knows? Yeah? No.
What? Okay.
What? Okay.
Yes. What? Okay. Use the formula we just derived from the thing.
Okay. What is it?
2 to the k.
2 to the k. Oh, right. So yeah, we could. That's right. We could use the formula. I was not thinking that, but yes, we could. 2 to the k. What was that? 2 to the k. What's that?
Minus 1.
Minus 1. All over 2 to the k. Okay, but here's the problem with that. Most of the time, when you have a sequence of partial sums, it will not be something easy to come up with a formula for. So yeah, we were in that particular example was very a very particular example where the sequence of partial sums was like it was possible to come up with a formula. Most of the time, it won't be. Most of the time, it won't be. So this works perfectly well. That's good. But most of the time, we won't have that, so we're going to need to use something else. How are we going to express the sequence of partial sums? Samuel.
Could you use summation of small s?
Okay, right. So we can use a summation. Summation because these partial sums are their own sums, right? Partial sums are sums in themselves. So to do a summation symbol, Control-Shift-S. Control-Shift-S starts a summation symbol for you. Now the kth partial sum. The kth partial sum. Does that mean that we're going to start with k equals 0, or are we going to end with k? The kth partial sum. So what's the fourth partial? Let's write out the fourth partial sum. What's the fourth partial sum? S of 4 is 1/2, right? Plus? So when you look at this sum, what does the 4 have to do with it? The 4 is what? What is 4 related to that sum? Is it the denominator of the second term? Is that what the 4 means? No, what does it mean? How many things we're adding together? So where's k going to go in this sum? He wants on the top, right? We're summing up k things, right? We're summing up k things. So I'm going to come up here, and for the partial sums, I'm going to make that k. So now, do we want k to be the index? We need something else, right? We need something else to stand for. First it's going to be 1, then it's going to be 2, then it's going to be 3, and then we're going to end at 4. So k is our ending value. We're going to need something else to march us through the terms up to the kth term. Does that make sense? So say use j. And then where's j going to start? 1, right? J starts at the first term, so we want j to start at 1, up to k. And what are we summing up? So what are we going to sum up? S of j or k? J. There it is. So this says, for the kth partial sum, start at 1, add the first term of the S sequence, then the second term of the S sequence, all the way up to the kth term of the S sequence, and that's the kth partial sum. And there it is, 1/2, 3/4, 7/8, 15/16, etc. Okay, so that's all on the video, if you didn't catch something, but summation is Control-Shift-S. And then you can just select the table, go up to table, add, if you need to add a formula column, meaning something that's going to be specified on a math line in GC, then you can add formula. If you just want a column and you're going to input yourself stuff into it, you can just add column. Okay. Questions on GC? Yes, please.
Since we're on the zeroth term,
I don't know if it'll work. Let's see. What happened? Yeah, by default, it said that S. Oh, well, what? Yeah, what is S0? Right. So S0 does exist. 1 over 2 to the 0, which is 1. So then now it's adding 1 to all of them.
But then you could make it okay.
So yeah, so it does affect. Do you see what's happening there? Yeah. Okay. Other questions? Okay. So that's GC. Again, so we're trying to balance here. We really want to understand sequences and series, but then we want to use this amazing technology that we have, right? So, but use it appropriately, right? So we want to don't just fall into one or the other. We want to understand, but then we want to learn how technology can do this quickly and easily for us. All right. So where are we here next? All right. So here's one. Let's do this one. So if I was to write out the series using summation notation, I could say that this equals, how do I start? I want to use summation notation. Well, that's just the sigma. And then when we're not in GC, we'll use I. I starts at what? And in this sum, it's going to go to? I want the series. It's nothing. I'm not talking about partial sums. I want the series. So I equals 1 to infinity. This means just go on forever. And then what do I need here? So what goes there that generates this series, just in general? I'm not asking for the answer, but what kind of thing would go there that would give me, what's that? I would need what? A formula for what? The formula for the sequence, right? It's the formula for the sequence. That when I stick that summation notation on that, then that sums up every term of the sequence, right? So you need a formula for this sequence. I'm going to write it out vertically. Okay, so that's 1, 2, 3, 4, 1, 2, 31, 69, 31, 23. Okay, so 1 gives 3, 2 gives 11, 3 gives 31, 4 gives 69, 5 gives 131, 6 gives 223. Harder, right? Not immediately apparent like some of the ones we've done before. So if you think you've got it, that's really good. But I'm going to show you a way that can really help you figure this out. And the way you can do that is you can make a new sequence of differences between consecutive values. We're going to see why this helps in a second. So from 3 to 11 is 8. 11 to 31 is 20. 31 to 69, 38. 69 to 131, 62. And what's this? 192? Or just 92, just 92. Yeah. Okay, why am I doing that? Well, let's just talk about something here. So what's happening? I'm getting how much, what are these like? From 3 to 11, 11 to 31, 31 to 69. These values are a principle that we've talked about in this class quite a lot, in fact. What does 8 kind of represent when you're talking about like values 3 and 11? Variation, right? Like it's how much this is varying from 3 to 11. So these are amounts of variation for a change of I in what? What are the changes in I? How much are the changes in I each time? 1. So look, and my independent variable is changing by 1. My dependent variable is changing by these values. So what are these values like? If these are the variation in my dependent for a variation of independent of 1.
They're your rate.
He's offering, is this like rate of change? Yeah, so these values are like rate of change, right? They're like how much your dependent variable is going to change for a variation of 1. All right, let's do it again. Now we're going to do it on those. So this is like the rate. Now we're going to find like the rate of change of the rate of change. 12, 18, 24, 30. Now we might notice something, right? So this is like the rate of the rate, and what do you notice about these values? What kind of function does this represent? 12, 18, 24, 30. What kind of function is that? Linear, right? Linear, constant rate of change. So then what kind of function do these represent? If this was the rate of change of these. Quadratic. Therefore, our original sequence, cubic. This is very helpful because what we can do is we can write out the cubes of I. So watch. What's I cubed? So this is now what's I cubed? 1, 8, 27, 64, 25. So now instead of trying to figure out what our sequence is from the I values, can we figure it out what it is from the I cubed values, and then we can have a fighting chance to make a formula here. So 1 gives 3, 8 gives 11, 27 gives 31, 64 gives 69. Can you come up with the formula for the sequence now? Can you do it? Some have done it. Think about it. So this was 2 more, right? This one is 3 more. This one's 4 more. Therefore, someone said I cubed plus I plus 1. Do you see it? Yeah, because it's this I cubed number plus 1 more than I each time. When I is 1, you add 2. When I is 2, you add 3. When I is 3, you add 4. So now we can write the series using we got it. So, pretty cool. You can use rate of change to analyze this series and then the sequence and figure out what the sequence is as a formula. By working your way, it's like taking the derivative, right? This is like taking the derivative, finding the rate of change, and continuing to do that until you have a linear function, figuring out what degree power your series was, and then using that power of I to help you. Any questions on that? So I think there's one maybe in the homework or a couple of that's a very helpful technique for. Any questions? Okay, so we're going to now talk about what's called convergence of sequences. So we're going to focus on sequences now for a little bit. So what do we mean by convergence and divergence of sequences and series? So an infinite sequence converges if all the terms after some place in the sequence become essentially indistinguishable from each other. So if we keep marching out on the list, and eventually at some point the values are so close together that we don't really care about the difference between them anymore, and it just stays that way, then this is called a convert. This sequence converges. And so that's what we mean by limit. Okay, so limit. The limit as I gets very large of those terms of the sequence essentially become the same number, right? Essentially, it just ends up this number that it's so the terms get so close to this number that we don't care about that minutia of difference anymore, and it just essentially becomes the terms of the sequence essentially become the value L. L, 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 L. If that doesn't happen, any other thing happens, we say that sequence diverges. So examples of diverges are the sequence just keeps getting bigger and bigger and bigger, or bigger and bigger and bigger. Negative. Another thing that could happen is the sequence kind of like just jumps back and forth between two or more numbers. The only way a sequence converges is if, when you get way out in the sequence, you essentially have L, 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 the same number over and over again, or something so close to it that we can't tell the difference anymore. So how about this one? Here's this very first sequence we looked at, the odd numbers, 1, 3, 5. Does the sequence converge or diverge?
Diverge.
Clearly diverges, right? These numbers just keep getting larger and larger and larger. They never hone in on a particular value. That's a good way to think about a sequence that converges. The values hone in. They hone in on a particular value. Okay, how about this one? This is the second sequence we looked at. And we figured out the formula for it was 2i plus 1 over I plus 1 squared, negative 1 to the I. So look, negative 3/4, 5/9, 7/16, 9/25, 11/36. So
We have to do a test.
yeah, so it's kind of, sometimes you can tell by looking at the first 5 or 7 or 10 terms. And that is a common strategy. In this case, you can't, right? So you can't really tell if it's really heading to a particular value or not. So we're going to look at this. And basically, this is a pre-calc problem when we were doing rational functions, because this is like the function. And we're going to take that alternating thing, we're going to take that off. For our purposes here, whether it converges or diverges, that doesn't matter at the moment. So asking whether this sequence converges or diverges is the same as asking if the limit as x goes to infinity of f of x exists or not. And that was something you worked on in pre-calc when you did rational functions. This is a rational function where we talked about that with the partial fractions technique, with one polynomial divided by another. And so, do you remember how you analyzed those? You compared the degree. Remember this? You compared the degree of the numerator and the denominator. What's the degree of the numerator? 1. Denominator is 2. So in this one, we have degree of numerator is 1 less than degree of the denominator. And when that happens and x gets really, really big, what becomes of that? Yep, this goes to 0 because here the biggest power of x is 1. Here the biggest power of x is 2. So when x is a billion or a trillion or a gazillion, right? This is always going to be x squared in the denominator versus x in the numerator. So imagine a billion. You'd have 2 billion plus 1, but you'd have 1,000,000,001 squared in the denominator. So do you see how the denominator is going to get much, much bigger, much, much faster? Because you're squaring the value versus just taking one of them. So that when you have large numbers of x, that's really magnified. So the limit is 0. And that means this converges, this sequence converges to 0. So now, does it matter that they alternate, plus and minus? No, that's fine. They're just, the magnitudes of these values are going to get closer and closer to 0. They're just, one's going to be positive, then negative, positive, negative, but it's still honing in on 0. So we have to go back and brush up on analyzing rational functions, limits of rational functions as x goes to infinity. This is what when you were doing like end behavior, like the horizontal asymptotes or slant asymptotes, that kind of stuff. What happens when the numerator is equal to the denominator? So let's just review fast this. If the numerator degree is less than the denominator, goes to 0. If the degree of the numerator is equal to the degree of the denominator, do you remember what the limit is? Yeah, so like 3x cubed plus 1 over 10x cubed minus x squared plus 6. That will converge to 3/10. It's the ratio of the leading coefficients. So and what about if n is greater than d? Yep, so then just like this one, the denominator exploded in size compared to the numerator. If this is the case, then the numerator is going to get really, really big compared to the denominator, and that will you'll have the sequence will diverge. Okay, so when your sequence can be written like a rational function, you're going to analyze according to comparing the degrees. Yeah, Tom.
Isn't 1 over x an exception from these rules?
No, it's not, because why do you think it is?
I remember hearing previously that 1 over x doesn't.
So you're thinking series instead of sequence.
Okay.
Yeah, we're getting to that.
Okay.
Yeah, we'll explore that, and we'll take a whole half class to talk about that. But when it comes to the sequence, 1 over x, the sequence 1 over x has the degree of the numerator is less than the denominator, so it goes to 0. Other questions? Okay, so that's how you analyze these sequences that are like rational functions. Another one here. Here's one. 2 to the I. So 1, 1, 4/3, 2, 16/5, 16/3, 64/7, which is 2 to the I minus 1 over I. Converges or diverges? So just compare what's happening with the numerator compared to the denominator. 2 to the ith power versus I. It's going to get huge, right? That's going to get really big compared to I. So you can see that happening as you write out the terms. The numerator is going to get much, much, much bigger than the denominator, so this diverges. Because that sequence is going to get infinitely big. All right, so let's talk about some common forms of sequences. The first is what we call a P sequence. A P sequence. When you have toddlers, you'll know all about the P sequence. All right, so 1 over I to the P. This is what it is, 1 over I to the P. So for a particular P sequence, P is a constant. All right, and then you have 1 over I to that constant, right? I is our index, 1, 2, 3, 4. So the question is, for what values, if we want to know when a P sequence converges or not, so we're asking for what values of P does I to the P get really big? And therefore this reciprocal gets really small. right? So values of p that make the denominator very large as I increases, those sequences will converge to 0. So here's 3 possibilities. So let's write these out here. So you see this and you think what? See this, think what? 1 over I cubed in chevrons? What does that mean? See? No. This has nothing to do with the question of whether it converges or not. What is this representing? In a word, what is it representing? What's that? A list of numbers. A list. You see this, you think, oh, that's a list of numbers. What's the first number in the list? 1. Second number?
1/8.
1/8. Third number? 1/27. Converges or not? Yes, definitely, right? This is definitely going to 0. P equals 3, converges. All right, what about this one? When you see this, what do you think in a word? A list. What's the list? 1.
1 over root 2.
Yeah, these are square roots, right? One half. Is this 1/2? Okay. Does it converge? Or?
No.
Let's just talk about square roots. What's the square root function? Doesn't it look like this? Does the square root function level off, or does it keep getting bigger? The square root of 1,000,000, the square root of 1,000,000,000, the square root of 1,000,000,000,000. Those numbers getting bigger and bigger? Sure. This always increases. Therefore, no, 1 over a list of values that get really, really big and never stop getting bigger converges. Do you see it? Square roots of numbers get bigger just like the numbers get bigger. They just get bigger slower, more slowly. The square root of 1,000,000,000 is way bigger than the square root of 1,000,000. And then the square root of 1,000,000,000,000 is way bigger than a square root of 1,000,000,000. So as I gets bigger, the list of square roots gets bigger too. So 1 over those square roots is going to go to 0. So when p is 1/2, we're good. What about this? When you see this, what do you think?
Oh,
A list.
1.
So 1 over 2 to the negative 2.
4.
4.
9.
What about this? 1, 4, 9, 16. These is essentially, this is the same thing as what? When p is negative, that's essentially just the power in the numerator, right? The positive power in the numerator. So when p equals 2, converge or diverge? Diverge. So for what values of p, so just from these 3 examples, could we come up with a rule for p that's going to make that denominator really large, and therefore the p sequence would be converged to 0? Yeah, it looks like when p is positive, right? That's what it is. So when p is positive, the sequence will converge and get closer and closer to 0. What about when p is 0? That's kind of a trivial case. When p is 0, what is our sequence?
1. It's going to start with 1.
1, 1, 1, 1, 1. So that converges. That converges to 1, a list of 1s, but it's kind of the trivial situation, right? It's not really trivial. Okay. So what do we say? We say that 1 over I to the p is 0 as I gets really big if p is greater than 0. Okay, another kind is called a geometric sequence. I will not be swayed by a large group. Geometric sequence. R to the I. So what is this now? So now your constant value is in the denominator. No, the base. And your I is the power. So now we're asking the same thing. For what values of R does Ri get really small, get really big, stay constant? Do something else. This is a list of ones. Same trivial thing as before. 2 to the I. What list is that? 2, 4, 8. So here, R equals 2. Converge or diverge? Diverge. 3/4. 3/4. 9/16. So we're squaring 3/4, then we're cubing 3/4. What about this? So it's like if you kept multiplying by 0.75 times 0.75, always taking 3/4 of the one you had before, right? You keep multiplying by 3/4.
They're going to get smaller, so it
Converges to 0. So when R is 3/4, converges. -1/5. So you're always, so what is this? These geometric sequences, it's just you keep multiplying by another value of R to get the next term in the sequence. So it's -1/5, and then times -1/5, then times -1/5. You keep, so you're essentially taking 1/5 of what you had before, and then it alternates, negative, positive, negative, positive. Converge? If you're always taking 1/5 of the number you had before, it's going to get really small and converge to 0. How about always multiplying by -3? -3 times -3 times -3. Diverges. -1. So we'll go -1, 1. -1, 1. -1, 1. Diverges. It's got to hone in on a particular value. So what could possibly be the rule for a geometric sequence? What values of R? Fractions, right? Between -1 and 1. I wanted to get through that so you can make progress on these in the homework. So these converge to 0 if R is between -1 and 1. It's like you keep multiplying by the same fraction over and over again. There's another one that converges also, but that's a trivial case. That's if R is 1, then you just get the sequence 1, 1, 1, 1, 1. Okay, start your homework. Have a great weekend.